and welcome to Lidnug's event by Ekberg on asynchronous programming. As always, we have a special thank you to our group sponsors, AuxWeb, Telvic, Pluralsight, Syncfusion. Without them, we can't really do what we do. So, as always, a great big thank you to them. You can find Lidnug mainly on, of course, LinkedIn, but we also have a presence on YouTube. YouTube being the place where this video will be recorded and posted to. We do have a presence on Facebook. We also have a presence on Twitter. And you can contact us by email for info@lidnug.org. As said, tonight's presentation is brought to you by Filip Ekberg. He's a Microsoft MVP. You can catch him on Twitter by the handle posted there on the screen. He is a Pluralsight author and has many titles to his name. Sorry, apologies there. I said he's a Pluralsight author with many titles to his name, and tonight's presentation will be on asynchronous programming in .NET. So, Filip Ekberg, without further ado, can I please hand over to you?
Thank you very much. I'll just share my screen here.
Okay.
There we go. Can everyone see my screen?
Looking good there.
Perfect. All right, so today's talk is about asynchronous programming, and I want to thank everyone for taking the time to come to this. I know it's early in some places and late in some other places in the world, so thank you very much for joining this talk. I'm Filip Ekberg. As mentioned, I'm an author, blogger, speaker, C# MVP, and just general geek. You can catch me on Twitter and send me any questions that you might have after this talk. I'm always happy to help out when there's C# questions around. So this talk is aimed for people that have maybe not experienced too much of asynchronous programming before. But if you've seen asynchronous programming, there will for sure be things in here that will be new to you, so stay tuned for that. It's also aimed at people that are kind of experienced .NET developers, because there will be a lot of .NET specific patterns and codes in here, so that will be good to have in your backpack. We do have a packed agenda. I will start off by talking about what asynchronous programming is, so you get an understanding of the problems we're trying to solve by introducing asynchronous programming, and kind of places where we might have seen this before. Then we'll talk about how to go from a synchronous application into being more asynchronous, and kind of the things that we are introducing in .NET to allow asynchronous operations. After that, we'll transition into looking at something that is even newer in .NET, and talk about two keywords that were introduced in the latest .NET version, being async and await. And with that, we're going to take a look at what really happens when we introduce these two keywords, because I find it's easier to understand what's going on in the application if we know what the compiler is doing behind the scenes. And I will add some time at the end for a Q&A, so if you have a lot of questions, please feel free to ask them. I will ask to have most of the questions at the end, but if there's anything that you want me to clarify, just ask for that and I'll try to answer it during the talk.
Mind if I just cut in quickly there?
Yep.
I've used the live meeting before. At the top of you'll find the panel for questions and answers.
Yep.
During the talk, if you want to drop a question in there, either Lidnug staff will answer that question or Phil will be able to answer it himself via voice. Okay, thanks, Philip.
Thanks. All right, so asynchronous programming, where might we have seen this before and why do we want to use it? Kind of the one biggest reason that I see for using asynchronous programming is to avoid unreliable applications. There are multiple different types of unreliability in applications, being either if an application crashes or if it pops up something that the user doesn't expect to see. And ultimately, we want to give users a better experience. And we want to be able to utilize resources that are available to us. That being, with the modern devices that we have today, we might have a phone with 4 cores, or we might have a computer with 16 cores, or something like that. And we want to make sure that we can concurrently work on different things at one time. So what is an unreliable application? The first thing that comes to mind to me is when an application crashes. I know that most of us have most likely seen this happen a lot of times before, especially being developers. When we're coding our applications, we more than once probably have them crashing on us. So this is not a good user experience, and getting an application crashed on us, we just hope that all the data is saved. So how do we provide a better user experience? Well, the first thing that I like to do is don't crash the applications. Might seem a bit easier than it is though. And we don't want to surprise the users. So that being not crashing the application, not slowing down the application too much to give them a bad user experience, not popping up dialogues that they don't expect to see. One easy way to solve this, or solve that we don't surprise them by crashing an application or locking up the application, is to show them a simple loading indicator. That could be if you have a web application, a desktop application, or a Windows Phone application, or other mobile application, you could show them a loading indicator when you're doing a lot of heavy work. So where does asynchronous programming fit into the picture with this? It sounds like it's kind of generic problems that we want to solve. Well, asynchronous programming lets us do processing before a current execution is done, such as reading or writing to disk. So imagine that you have a lot of data you want to load up from your disk. Then you don't want to lock up the application until you have that data available. So asynchronous programming is about allowing us to start off a process or start off an operation. And then when we are kind of done with that, we're notified that it's done. But meanwhile it's doing its work, we can go ahead and do something else. And if you're a web developer, you've probably seen AJAX or asynchronous JavaScript being used to do requests without kind of blocking the user from doing something else on your website. So it all sounds pretty much like parallel programming, but I like to use an example from my book where I talk about how to optimize boiling eggs. So imagine that you are boiling 10 eggs at a time. We know that each egg needs to be boiled for 8 minutes, but we can put all these eggs in the same bowl and boil them in parallel to each other. So the eggs boiling is actually a parallel process to each other, but the actual egg boiling is allowing me to go and do something else in the kitchen while this is being done. I can go and clean up or something like that. And then I set an egg timer to tell me you can now come back and take care of the eggs because they're done. The actual process of the eggs boiling is an asynchronous operation to what I'm doing. So the key thing here is that I set an egg timer. The timer will notify me when the eggs are done, and I can go back and take care of that. So we can combine asynchronous programming and parallel programming, and a good example of that is if I have my mobile application, I say that I want to start off an operation, an asynchronous operation, and that asynchronous operation might require to do some work in parallel. It might load some data first, and then it might process and sort and load on some other data in the background as well. So where do we normally meet asynchronous programming in our applications? I hinted before that we do that when we are reading and writing from disk. So any type of I/O operation will require us, or we can do asynchronous programming for that. Another big one is doing web requests. So imagine I want to load a large website, or I want to load the Twitter feed, for instance, and consume that in my application. That operation could be an asynchronous operation. So I could go off and say, hey, I want to load this resource from the web, and then I want to show this in my application, but meanwhile that is being loaded, I don't want to lock up my application. So how do we go from being synchronous to being asynchronous? I like to talk about this more in the sense of going from blocking to a non-blocking application. A blocking application is where we do a lot of work on the main thread in the application. So let's say that I have my mobile application, I go ahead and load a website, and the application just locks up. We're then presented with a screen telling us the application is being slow. Do you want to terminate the application, or do you just want to continue waiting for it? That's not really the best user experience, and it can tend to have the users force the killing of the application. So it's about freeing the main or UI thread quickly. And I just want to say this to start off with, it's really important. Don't force a block because async seems difficult. Async seems a bit easier now with the latest addition to .NET, which we'll see later in this talk. But I just want to tell you, don't force block because it's easier. It's not going to be the easier solution because you'll end up having more problems. So essentially, we want to free our UI quickly, and we want to give the users a really good experience. So asynchronous programming is not really a new topic. It's been around for a long time, and we've been able to do asynchronous programming in .NET for quite some time. Traditionally, we have two different patterns that we've used for asynchronous operations. We've been able to use something called the asynchronous programming model, which essentially relies on two different methods, one being begin and one being end. And we've seen this on, for instance, the stream reader, where we can do begin read and end read. And these methods take a delegate or an anonymous method or an action. So we can pass in an action that will be executed once the data is loaded, for instance. So in the case of stream reader, we say, I want to read this chunk of data. Whenever that is finished, call my delegate with the data passed to it. We've also been able to use a pattern called event-based asynchronous pattern, which we've seen for the old web client, for instance, or the background worker, where we go ahead and say, load this website, and once the website is loaded, we are getting a callback to this download string completed event. I want to introduce you to the task parallel library, which is another way for us to do asynchronous operations in .NET. I took this explanation from MSDN because I really like the way that they say how this works here. So it's about simplifying the work of writing concurrent and asynchronous code. The TPL was introduced in .NET 4.0, and it's there to help us write asynchronous operations. It's there to make it easier for us to consume, for instance, websites. It's easier for us to load things from the disk. And I'd like to jump into a demo showing you how the TPL works. So I'll go into Visual Studio. I've prepared a solution here, which is basically just a WPF application. Now, everything that I'll show you in here, it's not really WPF specific. It's just an easy way for me to show you the operations and show you how to use the task parallel library and how to do asynchronous programming. But the same patterns and the same methodology and everything works the same across different platforms and different devices. So if you're doing Xamarin for Android and Xamarin for iOS or ASP.NET, it basically works the same way. So all I have in this application is a button that says that I need to click this button. So we indicate to the user, just click this here and something will happen. So what I want to do is that I want to fire off an asynchronous operation when the user clicks this button. And the way that I do that using the task parallel library is by using something called a task. Now the task here lives in system.threading.tasks, and we have two different versions of the task to use. We can either use a task or we can use a generic version, which tells us that we can return something after this task is processed. So imagine this one here with the task of string being used for when we've invoked a web server and we get some data back. And the non-generic task is being used when we just want to run an asynchronous operation and we don't really care about an end result. So to fire off a new async operation, we can do something called task.run. Task.run takes a delegate or an anonymous method or an action, and we can simply fire off some work in here. Now imagine that we have a long running operation. We can simulate that by doing a thread.sleep. We can sleep for 2 seconds. And now if I run the application, you'll see here that it does in fact not lock up the application. As you see here, I can move around the window. I can click this button as many times as I want, and it doesn't lock up the application. If we were not using task.run here and not firing off an asynchronous operation, that would for sure lock up the application for the duration of the time that it took to load that. So imagine this being loading a long web request or loading a big file from disk. Now the other one that we might want to do is that we might want to return a value once this is done. So again, imagine that this would invoke a file on the disk or it would invoke a web service. We might have a return value after that. So also notice here that I don't have to use the generic task. I could do that if I wanted to, but I don't have to because there's a generic version of the run method here as well, which it will just automatically use if I don't specify that. So now how do you get this result from this task here? You might imagine that you just do var result is equal to this task because you think that this will just give you the result in the end. But in fact, it will not. You will get a reference to the task here. So we could say that this task.run here will return the task that is currently processing, but we need to get the data somehow. And one way to do that is by saying after this task has been completed, or we can block here until the task is done by saying .result. Notice what happens now when I run the application. I click here and it locks up the application for 2 seconds. The problem here is that we are telling this application to block until this asynchronous operation is completed. So what result is doing here is basically the same thing as if I were to call the method called wait. Wait will ensure that it waits for the task to complete its execution. And that basically means that if it takes 2 seconds to run this operation, it will wait for that to complete, then it will return the value and it will give us the result. So it will block the UI thread here until that data is available to us. So again, we're kind of getting a bad user experience here. And imagine that I want to add this result to my UI somehow. I might want to change the content inside my button to show hello world instead. So what's the other way for us to get the result without blocking our application? Well, let's get rid of this var result here and add something called a continuation. Now a continuation is a way for us to go back once we've started off an asynchronous process and say, once this is done, I want to continue doing something else. So I can add a continuation by saying this task needs to continue with something. And this continue with method takes an action as well. And into this action, it passes the task that just completed. So I can say the task that was just performed or just completed, I can use that in here. So we could say var result is equal to task.result. And if I put a breakpoint in here and run the application using the debugger attached, and I click this button here, we see that it doesn't lock up the application. And we see that we get the breakpoint in here and we do have the task result in here. So this is a good way for us to get the value out of this execution without blocking the application. However, now I want to change something on my UI. I want to say that my button, the content, which is the text that is displayed, will be whatever the result is returned from that task. So ideally when I do this and run the application again, and I click this here, hopefully that will work, and it doesn't. For some reason this doesn't work. So if I rerun the application and put a breakpoint in here, I click the button. After 2 seconds we get into that, and now we can see here that we're getting an exception. And the reason for that is when we are inside this continuation, remember that the task fired off an asynchronous operation. That asynchronous operation is most likely being handled on a different thread, and the continuation is also handled on a different thread. So we are trying to do cross-thread communication by saying, hey, I want to change the content on the button, but that button lives on the UI thread, or the main thread of the application. So we need a way to tell the UI that it needs to update. We need a way to say that, hey, I want you to update this only on the UI thread. So we need a way to invoke the UI. And in WPF, that's done using something called the dispatcher. On Xamarin for Android, it's done using something called run on UI thread. Xamarin iOS, it's done using run on main thread. And in Windows Forms, it's different as well. So this invocation on the UI, that kind of differs a bit on each different platform, but they do have one thing in common, and that's that they're all taking a delegate to run something on the UI. So we can use the dispatcher, and we can invoke something on the UI. This will tell it that it needs to run this on the UI thread. And as this takes an action, we can just pass the work that we want to do and move this part here up to the dispatcher.invoke. Now if I run this again, and I click the button, we'll see here that after 2 seconds, this text here changes to hello world. And that would basically be the same thing on all the different platforms, except that the dispatcher.invoke here, that part would change to, for instance, invoke on a main thread for Xamarin.ios. So I mentioned before that we don't want to give our end users a bad experience when we're doing asynchronous programming, and that one of these things being that the application crashes. One of the most common reasons for an application crashing is that we are deadlocking. So I want to show you a very easy way to deadlock, and I'll explain why it's deadlocking, and hopefully that'll become clear during this talk here. So imagine that we have this long-running process. We can simulate that by calling task.delay. So I'm going to delay for 1 millisecond here. So this fires off a new async operation that simulates that it's loading something for 1 millisecond. Now I want to say that I want to continue with something. So I just want to continue with some work when this is done. And for now, this all looks good. This should just work out of the box. But what happens if I force this to wait? What happens if I add a wait down here and say, I need you to wait here, which is blocking the UI thread, until the operation within continue with and until the task.delay is completed. If I run the application, you'll see that it still works. It does not deadlock the application, which is so far so good. But imagine that we're not really sure what's going on in either the task or in the continuation. We don't really know what kind of operation is being executed. Let's say that the continuation for some reason, or the task for its the asynchronous operation in the task, isn't trying to invoke the UI. So we can say dispatcher.invoke. What do you imagine would happen here? So for this part to finish or be marked as completed, this part here needs to be done. So for the task to fully be completed, we first need to invoke the UI. But down here, we're blocking the UI until the task is finished. So let's run this and see what happens. I'm going to click the button, and I'm going to try to use the window. I'm going to try to move it around. I'm going to try to click the button again, but nothing happens, because now we just deadlocked the application. And of course, the reason for that is because we are blocking the UI until the task is done. But the task cannot complete until it invokes the UI, so there's a deadlock. They have no way of telling each other that they're done, or they have no way of finishing their work. All right, so finally, before we go back to the slides, there's one more thing I want to show you with the tasks. What happens if we do task.run, and we have an operation here that is simply throwing a new exception? If I run this here, nothing happens. So that's because when there's an exception thrown within the asynchronous operation, the task itself will take care of that, and it will get a false state. So the way that we can get that, we need to validate the task. And to validate a task, we need to wait for its completion. So one way is by calling wait and force this to block and force this to validate that the task in fact did not work. So you'll see here that we just got an exception by clicking the button. It's telling us that it stopped working. But as I mentioned before, we never want to force our applications to wait for something to finish. We never want to force our asynchronous operation to block our UI. So a way to fix this is to set up a continuation again. This takes the task that just completed, and we can ask in here if it's faulted. You see here that we have is completed, is cancelled, is faulted. So we can check if this is faulted, and we can set a breakpoint in here. Click the button, we see that we get the exception, and inside the continuation we can see that it's in fact faulted. So looking at how this works later on in the talk, we'll see how it becomes easier for us to validate our tasks. But basically we need to wait until the entire task has been executed and make sure that it's processed correctly. Okay, so let's head back to the slides. So to summarize the demo that we just saw, we saw how easy it is for us to start off a new asynchronous operation by using the tasks. We saw that we can block and wait for a result, even though we might not want to do that, so we introduced a way to get the result without actually blocking the UI. We saw that we can either crash the application or not have it do anything by trying to invoke the UI from a different thread, but we saw how we can do proper invocation on the UI or main thread from a continuation in the task. We did see that it's pretty easy for us to deadlock an application by simply trying to cross-communicate and block the UI while trying to communicate from the asynchronous operation back to the UI. So kind of something to take away from that is to never do .result or .wait if you're not doing that inside the continuation. We did see how we can notify or be notified about a task's failure by checking that inside the continuation of that task. Right, so I want to jump into looking at async and await. I want to introduce these two new keywords which are kind of meant to be added to make it more simple for us to write asynchronous applications. Since looking at the pattern lately, we have much more rich clients with more smartphones coming around, and we need to understand the concepts of asynchronous programming and how to give the end user as a good experience as possible. So with .NET 4.5, we got two new contextual keywords, which is async and await. This basically means that when we add these keywords, a lot of things will happen behind the scenes. It does hide a lot of complexity, and it's really important to know what's happening when the compiler sees these two keywords. So it means that when it finds the async and await keyword, it will do a lot of work inside the compiler to make a lot of code for us. So this doesn't only hide complexity, but it makes our code more readable. Imagine that we had to write all the code ourselves that the compiler generates. That would add a lot of noise inside our applications. So the good part here is that we get a lot of more nice and readable code, but it also makes the code a lot more fragile. That means that it's easier for us to deadlock applications, it's easier for us to end up in states where we don't really know what's going on, and it just adds a lot of complexity, and we need to keep that in mind when we're using async and await. So the keyword async is used for methods. It's used to indicate to methods that they are being executed as an asynchronous operation. And what happens is that when we're indicating that our method is asynchronous, it takes the entire method body, and that will be executed in something called a state machine. The state machine is used to handle the state of the current execution. It's used to keep track of the current asynchronous operation, so it kind of knows where to do the continuation, and it knows where all the tasks are being executed. As it sounds, like this really does add a lot of overhead and complexity, and it's important to know what's really going on when this is happening. One thing to point out here is that if you're using async without the await keyword, you're doing it wrong. You need to use await and async together. They need to be used in the same context. Now, interestingly enough here, if you use the await keyword without marking your method as async, you will get a compilation error. But if you're marking your method as async and not using the await keyword, you won't get an exception, but Visual Studio will probably warn you that you are not using these two together. So it's important to note here that even if you mark your method as async, it will not mean that everything inside your method will run asynchronously. It will in fact you can be sure that it will run synchronously until you have a task that you are awaiting. So async and await needs to be used together, and there's no guarantee that all the code inside your method body will be executed as an asynchronous operation. So where do we use the await keyword? We know that we can mark our methods as being asynchronous, but where inside our method body do we use the await keyword? Well, if we have a task, for instance, task.delay, we can say that we want to await this to finish. And that means that everything after what we are awaiting will be inside a continuation. So instead of doing the .continue with on a task, you simply say, I want to await this task to finish, and then everything on the next line or after the semicolon will be executed as a part of the continuation. And it also returned to the caller with a reference to the task that is currently being executed. So what you can do with that is that if you have an await keyword, that will return to the caller, and you can still track the progress of the entire asynchronous operation. So as a difference from how the continuation works with the continue with on the TPL, the continuation with async and await will be executed on the main or UI thread. For instance, if you have actually will be executed on the caller thread, which is in our case is going to be the main or UI thread. But if you have a task in a task, that would mean that it would come back and run the continuation on the first task that you're executing. And if you want to get a result of an operation, let's say in our case we had task.run and then inside that we just returned hello world, using await will give us the result of that. It won't give us the reference to the task and then we have to do that result ourselves, but it will strip all of that out and will simply just give us the result. So let's take a look at how we can use async and await in one of our applications. I'm going to head over to Visual Studio again and I'm going to use this WPF application. And the first thing that I want to do is I want to introduce a new method inside this application. I'm going to call this method runAsync because I want to properly name my asynchronous methods by appending the name async at the end. So let's just do public void runAsync. We haven't indicated that this needs to be executed as an asynchronous method yet. So the first thing that we need to do is to add the async keyword. And when we are adding the async keyword, we also want to change what the method returns. We never want to do async void because we'll talk about that later, but that basically means that you don't have any way to track the asynchronous operation. So if we do async task here, what happens is that the state machine will give us a way to track the asynchronous operation. And now we're indicating that everything inside the method here will be executed within the state machine, and we can do things with tasks in here and run things asynchronously, and it will give us a lot more readable code, hopefully. So I said that we need to use the await keyword together with the async keyword. So now imagine that we have our task here. We are simply doing a task.delay. Let's do 200 milliseconds. And then I want to say down here, before this operation is done, I want to say that I want to await the task to finish. That means that everything at this line here at the bottom, everything after the await task, that will be executed as a continuation. So we'll be back here once this task has finished. So the internals of async and await, they will make sure that after these 200 milliseconds are passed, and we've awaited that properly and know that there's no exceptions and all that, we'll come back to this part down here where you see the comment to continue our code. And also worth mentioning is that this will validate the task that is executing. We'll get to that later on as well, but that's a good way to think about the await keyword as well. It will validate the task, it will give us a result if there is a result. So let's look at how we can get a result out of a task. So let's change task.delay to task.run. And inside this anonymous method, I want to do a thread.sleep. And I want to sleep for 200 milliseconds. And then I want to return hello world. What happens down here now when I await the task is that it's kind of going to strip everything out of the task. It's going to wait for it to finish. But it's not going to block. So that's a good distinction to think about. Await will never block. It will schedule a continuation. So it's basically like saying .continue with, but it works a bit different when it comes to the internals. So this will give us the result. So we can do var result is equal to the result of our asynchronous operation. So this will not only schedule a continuation and say, hey, I want to come back here when this is done. It will also give us whatever we are returning from our asynchronous operation. So down here at the bottom, what happens if I do mybutton.content is equal to result? Well, as I mentioned before, we're going to be back at the calling thread when we are at this line here. After the continuation or in the continuation, we are back at the calling thread. So if I go up here inside my button, click, and I simply do run async, we're calling this from the UI thread. We are shooting off a new asynchronous operation. We are saying, come back here once the task is finished. We need to wait for this here and schedule a continuation. And then we are back on the UI thread again to add this to our UI. So if I run the application, I click the button, we see here that it changed to hello world after about 200 milliseconds. All right. So I just want to reiterate here that we are adding the async keyword to anything that we are running asynchronously. A lot of people have asked me during the years, what happens if I have a synchronous method? Do I need to name that as run sync? Let's just say that if you don't mark this as async, I'll assume that it's running synchronously. I'll assume that this is a blocking call, and I'll assume that nothing in this method will run asynchronously, and it will just block my application if I call it. So if it's marked as, if it's called async at the end, I know that I need to validate this and await this call. Something that I want to note here is that if we go up to our button click here, we could validate this, and we really should validate that. There's one thing that I want to mention here is that we need to do async all the way. I did mention before that we shouldn't use async void, but we need to do that to use the await keyword in this case, and we'll get to that later on why this is allowed. So we can do await here to await this processing to finish as well, because if there's an exception in here, we want to be able to validate that up here in our button click. Now what I want to mention here is that imagine that we say start loading indicator. We are waiting for the work to process, so 200 milliseconds in this case, and when that's done, we want to stop the loading indicator. That's a good way to give our end users a nice experience when they're using our application. All right, so there's one more thing that I also want to call out, and if we just get rid of this code here inside run async, what happens if there's something inside our task.run that we want to run asynchronously as well? So let's say that we have var results is equal to await task.run. And now inside this task.run, I want to run another asynchronous operation. Let's say that I have a task.delay. And after that, I want to return hello world. But I don't want to return hello world until the task.delay is done. So that would mean that I need to do an await here. But I can't do the await without the asynchronous keyword as well for the method. Now you're in luck because you can do asynchronous lambdas. So you can say that this is an asynchronous anonymous method, and using the await keyword will simply work in here. So that's a good way for us to do an asynchronous lambda expression or an asynchronous anonymous method. So let's head back to the slides again. So to summarize what we just saw here, we saw that it's easy for us to introduce these two new keywords. It's easy for us to kind of extend what we saw using the TPL and just add the async and await keyword to work with our tasks and to schedule continuations. And one thing that I want to show you before we, the last thing that I showed you before we headed on was to how we added things to the UI. And we did that by awaiting the result. So we had our asynchronous operation that kind of ran something for 200 milliseconds and then gave us a result. And we saw how we can use the await keyword to strip out the task and wait for it, and the state machine takes care of all that. And then when that is done processing, we get the result of that asynchronous operation. And we did see how we handled continuations by, after we've awaited the result, we got back to the UI thread. We could easily update the content of our button without doing the dispatcher.invoke, because we are back on the place where we first initialized our asynchronous operation. I want to reiterate how important it is to properly name our methods. We saw that it's easy for us to just name it async if it's an asynchronous processing, but we should never really name them sync if they're synchronous. We'll just assume that the method is running synchronously if they're not marked as async. And also an important thing here is that we saw that we can introduce asynchronous lambdas. And I do see this quite often, that people tend to forget that, and it's an easy way for us to validate tasks within an anonymous method. Okay, so let's jump on and look at what's going on behind the scenes. So adding async and await seems very easy inside our applications, but I've indicated that there's kind of a lot going on behind the scenes of these operations. And there's a lot of code being generated by the compiler, and we kind of need to understand what it's doing in order to use this properly. So what does appending async really do in our applications? I indicated before that it's generating a state machine, and this state machine is implementing an interface called iAsync state machine. Now the interface alone is not really important. What is important is that it has a method called moveNext, and we'll get to that in a little bit. The method body for our asynchronous method will be completely rewritten, and the original code from our method that we, for instance, if we have a task.delay, that will be moved into the state machine's moveNext method. So we have this moveNext method on the interface for the iAsync state machine, and our entire method body will be rewritten and moved into that. So this is where the contextual keywords come into place. They're keywords that don't really mean anything to the CLR, for instance. They're just there to generate a lot of code and for the compiler to interpret what's going to happen. So in this example here, we are creating a new asynchronous method. We're marking this as async, and we have a task that we can track the asynchronous operation. We're then setting up a new variable, var x is equal to 10. We are awaiting a task to finish, which is simulating that we are running something that takes 2 seconds. And then at the bottom here, we are back in the continuation and in the caller thread and doing a debug.writeLine of x. So what happens when we run this through the compiler? What is really generated when this is being compiled? Well, it will turn into something that looks like this. So the method body of run async, if I just flick through these 2 slides here one more time, you'll see that the async keyword at the top is being removed. So if we decompile this code here using reflector, for instance, we'll see here that there's no async keyword. The async keyword is gone. It has, however, generated a state machine called runAsync d__1, and that state machine is initialized with a builder and an initial state of -1, and then it's saying that it starts this. And look at the bottom here. We are returning a task that is a reference to the current asynchronous operation. So what happens here is that since we are saying that this will return a task, we are getting the task that is being processing, that the asynchronous operation is processing. So where's all our code? Where's the var x is equal to 10? Where's the await? Where's the debug.writeLine? Well, that's inside the state machine's moveNext method. So this is the moveNext method of our state machine. And what's going on here is that we are first checking the initial state. We can then see that we have this .x 5__1 is equal to 10. So that's our initialization of our x variable. And then we see here that we have our task.delay, and it's being awaited. So what's happening here is that we are getting the awaiter to check if the operation is completed or not. What I want to mention here is that the state machine, all this code here, is being executed on the caller thread. So as you saw here, it's simply doing calls to these methods here, and it's not being wrapped in a task.run or anything like that. It's actually code that's being executed on the caller. So the only code in here that is being asynchronous is this task.delay up here. So where is the continuation? Well, take a look at the bottom here. We see that we have debug.writeLine. So at the end of this moveNext method, we can see that we have our continuation, and this is being processed on the caller. So what happens if we mark something as async void? Can we do that? We did see that I just did it before just to validate that our task was completed inside our event handler. But can you use async void? I'm going to say no, because it's really not a good plan to do that. The only reason that it's allowed to do is due to events, because we have the delegates to match our events, and they are all void methods. So we can't simply change that to task. So it's only allowed due to events. So if you're ever doing async void when it's not an event, don't. So we have the same method here. I simply changed the method signature to async void instead of async task. The method body is all the same. The rest of the method signature is also all the same. So what happens when we do this instead? What's going to happen inside the state machine? Well, if we take a look at the compiled code, there's no way for us to track the progress of the asynchronous operation. First of all, it's using another type of builder. It's using an async void method builder, which means that it knows that this is a void method. And looking at the bottom, on the previous example, we saw that it returned a task with a reference to the asynchronous operation. But we don't get that in this case. So how do we know that the task finished processing? How do we know if there's an exception inside the state machine? Well, if there's an exception, we will be notified by that. We will know that there's an exception because the application will die. So how do we fix that? How do we fix our application not crashing when there's an asynchronous void method? Well, there's two ways to do that, or there's multiple ways to do it. Make sure that your application never throws an exception, which is probably easier said than done. So the more simple ways to change your void to a task, which is not really viable for an event handler. So inside an event handler, you just have to make sure that the code that you are running, if it's an async void event handler, just make sure that it's not throwing an exception. We still need to validate the tasks, and we'll see here in a bit how we validate the tasks. And we did kind of hint that before when we did the throw exception, and I said that you need to do .wait. But since we can now use await, that's a way for us to validate the tasks. So let's have a closer look at what async and await is actually doing when we are using this code in our applications. So I'll head over to Visual Studio again, and I want to just change this run async method body, and I'm just going to remove a few things in here to make it easier for us to get off on a fresh start. So let's say that we have an await task.delay and we are just delaying for 200 milliseconds. I want to add this in here. It's not really important to the demo itself, but I want to make it obvious to you that await and async should always be used together. Now, once this is awaited, I want to throw a new exception. If we just run the application like it is now, we're running our run async method in here. I'm going to start off the WPF application. I'm going to click this button here, and you'll see that nothing really happens. Just as when we did task.run and threw a new exception in the TPL demos, the exception down here will in fact be caught inside the state machine, and it will be set on this task up here. So a way for us to validate that would be to await this call up here as well. I do want to show you, however, what happens if we just rename this to async void, or change the method signature to async void. If I click this button here now, the application will crash. So that means that the call to run async is throwing an exception, right? So I should be able to just simply try and catch this. What do you imagine will happen when I run the application now? Let's run this here, and I click the button, and we see here that I'm doing a call in here to run async. I'm trying to catch the exception, and I'm going to click the button, and the application still crashes. So why is it doing that? Well, the reason for that is because when the state machine has no way for us to track this error, it has no way for it to know where to put the exception. So it will set that on the calling thread, which is the main UI thread in this case. So the application will think that the entire application crashed, and you have no way of recovering from that. So if I change this to async task instead, how do I catch the exception up here? Let's put a breakpoint inside the catch block here. You saw before that simply calling this when there's a task, there's no way for us to catch that. We need to mark this as async void, which is a bit twitching my eye a bit, but we need to do that since it's an event handler. So now that I'm doing await here, I'm validating the task that is running this operation. I'm wrapping this with a try catch block to catch any exceptions that will occur due to this operation. So let's run this without the debugger. I click that, and need to run it with the debugger. I'll click that, and we see that we just caught this exception. So there's no code in here that would really fail this now, so there's no reason for it tearing down the application because this is marked as async void. So if you have to do async void for your events, just make sure that you have no code that could fail. I want to show you another way which is a really easy way for you to do a deadlock. Imagine that I call run async. Remember that I said before that the state machine itself is running on the caller thread. It will get the awaiter on the caller thread and check the state. What happens if I force a block on the caller thread, which in this case is the UI thread? So I'm saying run the asynchronous operation, and the state machine itself will be executed on the UI thread, but we are forcing the UI thread to block here until this is completed. But how will the state machine be able to check if it's done if we are blocking, right? So this is a very easy way for us to cause a deadlock. You see here that I can't click anything anymore. I can't move the window or anything like that. So we have to go back and kill the application. So doing a .result or .wait when you have an asynchronous method, whenever you call something called run async, if you do .wait or .result, expect that method to fail. So if I really want to block here, is there a way to do that? Well, since the state machine is running on the caller thread, how about I put the state machine on a different thread? What happens if I do task.run? This is a neat little trick here. What happens if I do this? I start off an asynchronous operation from my UI thread. I block the UI thread until this operation is completed. Inside this operation, I'm running the state machine, and the state machine is checking if the asynchronous operation is done. So I'm not really blocking the state machine itself. So if we run this here, and I click the button, you can see that it stopped working because there's an exception down here. Let me just get rid of that first. Let's run that. There we go. So I can click the button here, and you see that the application is not crashing. It's not blocking, it's not crashing, it's just working. So the reason for that is because we're blocking the UI thread, but the state machine itself is communicating back to the asynchronous operation that I started by doing task.run. So we're kind of creating a proxy task here to handle our state machine, which will then make sure that our other asynchronous operation is being executed properly. So one more thing that I generally do see quite often is the usage of too many state machines. And I've seen this so many times. So let me bring in a few lines of code here and talk you through what's really going on here. I'm going to introduce a new class that I call Resource Manager. The Resource Manager that I want to introduce here is being used to load resources from my local disk. So let me just talk through this code here. Just going to clean this up a little bit here. So imagine that I create a new instance of my Resource Manager. I say that I want to load resources asynchronously because this is the only public way for me to do that. I cannot call the other private methods down here. So imagine, let me just make this a bit bigger. So this in its turn says that it's an asynchronous operation. It's awaiting the result from load resources from location async. So it's going to load something from resources.dat. If I go down to this method here, we can see that it's simply saying this is a private method, it's asynchronous. It's awaiting the result from load resources from location with permissions async. That's a mouthful. So it's just passing string.empty to this one here. And if we go down to this method, we can see that this is where it's really happening, right? We have the first await keyword that really makes sense because we're awaiting a long operation. Imagine that being a web call or loading something from the disk. And then we are returning hello world. So the reason we are doing task of string up here is because at the end of this operation, we are returning a string from this context. Now we're doing the await keyword here, so we will be returning to the caller at this point for it to have a reference to this asynchronous operation. So we'll return up here, but we have another asynchronous operation up here, or we are scheduling a continuation. So we are waiting for that in the load resources from location async as well, and then we have this other await keyword as well. So what do you imagine happening when we're doing this? We have an async keyword here, we have an async keyword here, we have an async keyword up here. So what are we really trying to do here? We are trying to get the string back to the caller. Now the only way that we can get the string back to the caller is by returning the hello world from down here, and the only way to do that is to await the result itself. Well, the problem here is that we are using the await keyword everywhere, and we are expecting to return task of string in all of these methods. If I just compile this here and head over to reflector, let's see if I can open that up. If I refresh this here, we'll see that we have our resource manager, and we have one state machine for load resources async. We have one state machine for load resources from location async, and we have one state machine for load resources from location with permission async. So that's kind of a bit too many state machines in my opinion. The only reason you'd want to have a state machine generated is when you'd want to schedule a continuation that really makes sense. In this case up here, for instance, it doesn't make sense to create a state machine because there's no obvious work after the continuation. Since we're just returning whatever we have here, we can simply remove the async keyword and remove the await keyword and still have the same return value for this method. Because we are getting the task of string from this method call, so why do we need to mark this as async and using the await keyword? And the same goes for the method up here. Why do we need to mark that as async and do the await? It's still an asynchronous method because we are in the end doing an async and await call, and we are returning a task of string. But we're still returning the same value, so we're not breaking anything in our applications. So if our application expects us to get a task of string, we can do this refactoring without actually breaking anything from the user's point of view. So if I recompile this here, I refresh whatever we have in here to see what we have inside our resource manager now, we simply have one state machine instead. So instead of having this complexity nested in more complexity and in more complexity, we just have one complex state machine here taking care of the work in the method that is actually doing an await. So we see here that it's easy for us to just refactor this into using less state machines. And one thing that I do see quite often is that just because you are calling something async doesn't mean that you have to use the async and await keyword. You can still just return that task to the caller, especially if you have a nested method call like this here. Okay, so let's head back to the PowerPoint. So to summarize what we just saw here, we saw that it's easy for us to swallow the exceptions if we're not validating that the tasks are completing properly. We saw how we can never recover from an exception by marking our asynchronous methods as async void. So something to take away from that is to never do async void. We did see how to force a block without deadlocking an application by kind of doing this proxy task. I saw someone writing the phrase proxy task somewhere, and I think I like that naming of that little hack. And we did see how we can deadlock, and how we can deadlock very easy by blocking the thread that is waiting for the state machine to notify that it's done. And again, we saw how we can validate a task and how we can kind of catch that exception if there's an exception inside the task that we are validating. And the validation with async and await is much easier and much cleaner than doing this with the continue with on the task parallel library. And finally, we did see how to avoid creating too many state machines by not appending the async and await keyword to every asynchronous method. We can just return that task if we have a nested method call inside our applications. So what about ASP.NET? What happens when we do this in a web application? We've so far talked about rich clients, and even if I have used WPF here, it's mainly WPF because that's easier to start and easier to just terminate when there's a deadlock. I could do the same thing with Xamarin for Android or Xamarin for iOS or Windows Phone or WinForms, for instance. But I just used WPF to make it easy. But the same patterns and practices and the internals work the same on the different platforms. So what about ASP.NET? If we do async and await in ASP.NET, that does not mean that it kind of terminates the connection to the client and then opens it up again when there's data available. It will keep the connection open with the client until the process on the server is done, and that means all the processing on the server. So the main reason to use async and await in ASP.NET is to allow processing of other things while some asynchronous processing is being executed. So we need to consider something called a synchronization context when it comes to ASP.NET. It's basically the same thing as thinking about the main or UI thread. The synchronization context is used to communicate between different threads and different contexts within one application. So let's have a look at how we can use async and await inside ASP.NET. I've prepared an ASP.NET solution here, and it's just an out-of-the-box ASP.NET MVC solution. It's generated the nice home controller and the nice views for us. So the first thing that I want to do in here is that I want to mark this as async. Now, when I mark something as async, we know that we need to return a task. It could be a task with a result, and in this case, I want to have a task that in its turn return the action result when it's done. And since async and await always need to be used together, we can say that I want to run something that takes a bit of time. So we can do await task.delay. Do that for 200 milliseconds. Now imagine here, I just want to reiterate that this could be an HTTP client.post async, or it could be load from a file async. It could be anything. I just use task.delay to prove that it's using a task and that it's simulating a lot of work. So we're telling the state machine here to run all this code inside the state machine. We're waiting for a task.delay to finish, and once that's finished, we are back to return the view to the caller. So let's put a breakpoint up here, and actually let's increase that to 2 seconds. There we go. And I want to put a breakpoint at the bottom as well, just to make sure that we are getting a 2-second delay here. So you see here it takes 2 seconds, and then we're back to return the view. And then we can look at the website to see that it in fact returns what we expect it to. So it doesn't return the actual task to the website, it returns the result that we expect. So how do we do a deadlock in ASP.NET? Let's remove async and task up here to get back to the original state. And let's say that we have our famous run async method. Now this run async method here might just do an await task.delay again to simulate that we're doing a lot of work. And I'm going to call this up here in the index. And one thing that I actually do see quite often is that if we're invoking something asynchronously, if it be it loading a file or be it loading a web server, website, sorry, people do this. Now this doesn't return anything, so that won't be a task of string, but this is a basic pattern that I do see, and if you do that in this case, it will deadlock. So let me simulate the force block here. So this will force the synchronization context here to be blocked until that is done. So if we put a breakpoint here and a breakpoint here, and I start this with the debugger, and I click F5 here just to continue on, you'll see here that we will never hit the second call here. And if we were to head over to the website, you'll see here that it's just loading and waiting for localhost to finish, and it will wait there forever, or until it times out, depending on the browser. So how do we fix this? Well, it's basically the same thing as we've done previously. We need to avoid capturing the synchronization context or the UI thread, or we need to just avoid running the block on that place. So we can do task.run and create our little proxy task here. And if I put a breakpoint here now and a breakpoint here, run the application, we'll see that we are in fact going to block here for 2 seconds. And after 2 seconds, we will be returning down here to return the view to the caller. So this kind of just proves that we can do the same kinds of things in ASP.NET, and the same kind of patterns and practices are the same when it comes to web development and rich client development. So let's head back to the PowerPoint. All right. So to summarize this here, we saw that we can easily do async and await in ASP.NET, just as we did in WPF, and this could be applied to other platforms as well, wherever you can run .NET. Now I do want to say that deadlocking, for instance, is going to be different on one platform, it's different on Android, but basically the same patterns and practices for everything else is the same on all different platforms. We did see how to avoid the deadlocking in ASP.NET by avoiding capturing the synchronization context. And it's basically the same thing as we did in WPF, where we just avoided locking up the UI thread and avoiding locking up the state machine to notify us for completion. So a few considerations to take away from this here is to don't mark your void methods as being asynchronous methods, because that's going to end up being a big problem for you. Tasks do swallow exceptions, so that's really something you need to keep in mind, and you need to validate your exceptions whenever they occur inside your applications, or you need to validate the tasks which could have exceptions rather. Doing .wait or doing .result is an easy path to deadlocking your applications. So you really want to avoid forcing a block, and if you need to force a block, you can simply do the small hacks that we saw before by doing the proxy task. Again, follow the naming convention. I see quite often that people tend to just call their methods run or my method or whatever, even if they're asynchronous, and I think to myself, like, why is this so quick? It shouldn't be that quick. And then it turns out that the application is actually doing something asynchronously, and you don't really know what's going on without knowing the exact implementation of the method or what it returns. Because not everyone will check if it returns a task or not, even if you should be thorough and do that. Adding the async keyword at the end kind of helps the developers know what they're working with. I didn't show this, but I want to tell you not to lie. We were probably all told when we were small kids that we shouldn't lie, and we shouldn't do that in our applications as well. We don't want to wrap our synchronous methods in a run async or task.run and call it async. Because what happens is that if you have a synchronous method, the person that implemented this synchronous method might expect it to be synchronous and might do a lot of invocation on the UI, which means that you could possibly end up deadlocking your application. So what I'd suggest you do instead is just copy the method body of the synchronous method and paste that into a new method body and call it async, and make sure that everything inside that method is being run asynchronously. And with async and await, the entire continuation is on the calling thread. And that's an important distinction when it comes to comparing with task.continueWith. So I want to recap everything we've kind of learned here today and everything that we've looked at to just give you a nice overview of what to think about and how this really works. So the problem we are trying to solve is to avoid unreliable applications. We want to give our end users a good experience, and we can do that by introducing asynchronous programming inside our applications by simply relieving the UI of all the heavy work. We've seen asynchronous patterns before in different types of applications, especially if you've done web development and you've used jQuery, for instance. In this case here, we are posting something to a web page, and when this post is done and there's data returned to us, we're getting back to callback here with the result of that operation. So what is a task? We looked at what a task is, and we saw that we can invoke and start a task in different ways. We can start a task by doing task.run, and we can then pass this with an anonymous method, and it will just run this operation for us asynchronously. And we saw that we have a different way of also starting off a new task by saying that we start a task that will in its turn return a value. So we have this generic task to indicate that we are getting a value return in the end of this asynchronous operation. We also talked about how we can and how we have solved asynchronous programming before by using either the asynchronous programming model, where you do begin and end methods, for instance with a stream reader, where you do begin read and end read, and you also pass a delegate to be invoked when this operation is completed. We also saw that we can use the event-based asynchronous pattern, which is seen on the web client and on the background worker. So you get notified when the data is completed or when the operation is completed by having an event invoked. And we saw how we can continue work after a task is done processing its asynchronous operation. We saw that we can use the continuation by using the TPL's continue with method, which is simply expecting you to have an action that takes the task that was just completed. And then we can do our work inside that continuation. And with async and await, we saw that it gets a bit easier. We can simply await a new task that is currently running an asynchronous operation. And after that, we can do a, for instance, debug.writeLine, and we're kind of have this more linear and sequential way of writing and reading our code, which makes it a lot more readable. So how do we get the result of an asynchronous task? Well, we saw that with the TPL and when we're using continue with, we get the task passed into that as an anonymous method, and we can do task.result in there, and in this case, it will not be blocking the caller. For async and await, it again gets a bit more linear and it gets a bit more cleaner. We're saying that we are awaiting a task to run, and the await keyword will take out the result of that asynchronous operation and put that in whatever variable that we are indicating it to store that in. And then we can, of course, again, use that on the next line in, for instance, debug.writeLine. We saw what really happens when we mark something as asynchronous. We saw that we are generating this heavy state machine, or depending on the code that you have in your method body, could be quite heavy. But the state machine adds a bit of overhead, and it adds a lot of code that you really need to understand to know what's going on behind the scenes and kind of what goes on inside your applications. We saw how the continuation differs from the task.continue with. So we have these two different examples where we are either doing task.run to start the asynchronous operation, and then we have the continue with on that task. And that continuation is executed on a different thread. Which thread it is isn't really important, but what is important is that it's not executed on the caller thread. For await, we are back on the caller thread whenever that continuation occurs. So as we saw before, if we compare these two here, the big difference is that, first of all, it looks more linear to do the second one, and the second one will be executed inside the state machine on the caller thread. And that's an important distinction to make. So what really happens when we use the await keyword? We just know that it kind of gives us the result, but it also marks a continuation. So it returns from the current execution, it returns that to the caller with a reference to the currently executed asynchronous operation. And what happens with the await keyword is that, of course, we do get the value after its continuation is being invoked, and that's really one of the more important parts of that. So what code is generated when we mark something as async inside the state machine, that is? Well, we do get this heavy code here that it's kind of hard to just read out of the box, but looking at the top here, we have our task.delay for 2 seconds. We're getting the awaiter to confirm that it's either completed, or we get back to this at a later stage to check if it's done at that point. And if it's not done, we just return from the state machine and we get back to this this is kind of done in an iteration. It checks it again and checks it again. And then at the bottom here, when we are done, when the task is completed, we will simply be back on the caller thread and we can run our continuation. So what's the problem with appending something like async and await to our application? What's really the biggest issue with doing this in one of our applications? Well, adding these two simple keywords really means that we do get a more complex and confusing application. Just naming something as with the word async at the end, like run async for instance, we don't really know what the implementation of that method is doing, right? But if we mark it as async and we use the await keyword, the caller needs to be cautious about how it's invoking that. For instance, it should never do the blocking calls, it should never do .wait or .result, because that would lock up where the state machine is running. So with these two keywords, we do really get a lot of things behind the scenes for us, but we also need to be cautious about how we use that. So we do need to invest time in learning what really happens behind the scenes here, because our code does become more fragile. I do see quite often that developers tend to use async and await on a lot of places, and in a lot of cases they're lucky because it just works. But sometimes you just end up having an application that seems like it's just loading forever, and you didn't notice that there was actually a deadlock on a different thread. So imagine you start off a task, and then you're blocking the first task, so the second task can never complete, right? Because they have they're doing cross-threading to each other, but they're both deadlocking. So your application seems like it's loading forever. And that's a really common thing that I do see happening in a lot of applications. We also learned what the state machine is really doing, and we saw that it asks us, are we done yet? Like a little child, it asks us over and over again if we're done, and when we are done, or if there's an exception inside the state machine, it reports this properly. Properly being that if we have a task that it can report it back to, it will set the exception on that task that we're currently using to track our asynchronous operation. However, if we are using async void, there's no way to report that properly back to us, so it simply tears down the application. I think that's kind of a way for the compiler to tell us that it's not really a good idea to do that, and they're kind of giving us back for not doing this properly. So what do we do after a task is completed? That's also something the state machine is taking care of. It takes care of knowing the continuation. It takes care of knowing the current state of what everything is doing, hence the name state machine. And it runs the continuation on the caller thread, which is really something that I want to emphasize here. So why shouldn't we lie in our APIs? Well, imagine that we are wrapping a synchronous call in task.run. It could be blocking code, right? So if we do the dispatcher.invoke, or we are doing mybutton.content is equal to something inside an synchronous method, and then we're simply wrapping that in an asynchronous call, suddenly what happens? We'll get an exception because there's cross-threading going on, but since we might not be validating the new task.run, we have no idea that there's an exception going on. So the application might seem faster, but you are also getting a more unexpected behavior in your application. So your user experience might suffer if you're not 100% sure what the synchronous code will evolve into. So a developer might work on this synchronous method, and you might just wrap that in an asynchronous method, and everything works out of the box. It works nicely without doing any special tweaks. But then a few weeks later, the other developer that worked on this synchronous code comes back and changes something that invokes the UI again. The developer has no idea that there's an asynchronous version of this out there that is simply invoking this synchronous method, and suddenly the application behaves a bit weirdly. Now, of course, you could catch that in good QA, and you could catch that with good testing, but if you just know how to do these invocations and how to use async and await and how to do asynchronous operations, that shouldn't really come up in such a case. We also saw how to do this in ASP.NET and how ASP.NET handles asynchronous code. The synchronization context is captured, which is basically a way for the framework to cross-communicate between different contexts. And if this context is captured and we are forcing a block, that would kind of deadlock our ASP.NET application. So deadlocking does become easier, or rather as easy as it is on a WPF application, for instance. So by using task.run, we can avoid capturing the synchronization context. So we're kind of doing the same proxying as we saw in WPF by not doing this work on the main thread or using the synchronization context inside the task.run. So what are the most common reasons for deadlocking? That's something that has been on a reoccurring topic in this talk. And I like this illustration here of the cars that are kind of caught in this intersection where none of them can actually do anything. They could, of course, all of them could back up, but in programming, you can't really go backwards, you can only go forward. So we have a deadlock here where no one can go further. So in this case here, we're starting a task. When the task is continued, it needs to use the dispatcher to invoke something on the UI. Now we're forcing a block here to say that I'm going to block the caller or block the dispatcher or the UI thread here. So there's no way for it to call back to the UI and notify that it's done. And the same goes with the bottom one here, which is simply invoking a synchronous method. It might be marked as async, we don't know, but calling .wait here will for sure deadlock this application. So notice the pattern here. We're doing .wait, and it's important to never block your applications. I know that I might sound a bit, I'm saying this quite a lot, but it's really important because I see this happening all the time, and blocking your applications is never a good idea. And the user experience suffers. Even if it doesn't deadlock, blocking the application kind of gives the user a bad experience. So how do we avoid deadlocking an application? Well, there's actually one very, very simple way to avoid deadlocking. At least avoid deadlocking when it comes to the more simple scenarios like the state machine and the cross interaction with the UI that we saw there. It's to do async all the way. It's to do async from the the bottom of the asynchronous call all the way up to the UI thread, as we saw in the event handler for my button click. We used async all the way. Even though at the top level we have to do an async void, we can just make sure that there's no code in the event handler that will cause an exception. So when we are calling all the way down, we are either awaiting properly all the way down if we need to, or we're just passing that task up to the UI thread, and we're awaiting that at the final stage. So really do async all the way up, and if you really cannot do that, you have the hack of doing a proxy task to force a block, but really avoid doing that if you don't have to. So I think we have some time left to do a Q&A. We might have 10-15 minutes. I'll stay around as long as possible. So before we do that, do we have a few questions in?
Yeah, if everybody wants to post any questions they want now to the Q&A. But just start off with, we have one from Kareem, which is, performance-wise, is there any benefit to prefer continue with to async or wait?
That's a very good question. So you're asking if there's any performance difference by doing continue with or using the await keyword and using the async and await. Not that I've noticed. I haven't seen any performance penalties by introducing async and await. It does add a little bit more of code, but the code that inside the state machine isn't really that heavy, so it will not really do any performance penalties.
Okay, great. Hope that answers your question there, Kareem. This one, we have one from Brian here. Do you need to see being the next step of async? What do you see being the next step of async programming, and where does the .NET framework lack in current support?
So the question is, where do I see async going in the future, and what the .NET framework lacks? That's a very good question. I think it's going into a pretty good state right now. Like looking over, traditionally we've had ways to do async a long time, and it's evolved into a more simple and linear way of writing this. So we kind of write our applications as we expected would happen, but there's still a lot of fragile code going on behind the scenes. So what I'd like to see in the future is that for the cases where it just tears down the application when there's, for instance, async void, I'd like it to be more easy for us to get out of that without actually crashing the entire application. There's, of course, reasons for that, that implementation, but I see that it's becoming even more easier in the future, and that adding these keywords might not impact too much on those kind of things.
Okay, awesome. Next one from Peter. Oh, by the way, Brian says, thanks for the great presentation.
Oh, thank you very much.
Peter asks, what would happen if I did async with async? Could I actually cause an inception-like scenario?
If you do async and async, you can do nesting async calls, like we saw in the resource manager that I showed. You can have nested async calls, but you cannot use the async keyword twice on a method. That wouldn't make sense.
I've had a few playing about with core myself. I've had like 3 awaits in the line just for the fun of it. That makes quite interesting code to play with. Just while waiting for other people to post. Oh, wait, there we have another one from Kareem. Does async and F# differ in any significant way?
Does F# and C# async differ in a significant way? Yes, they do. I'm not too familiar about the async in F#. I do know that F#'s had the async keyword for much longer than C#, and they've had a way to do asynchronous programming like this for a longer time than C#, but I'm not really sure I'm the person to answer that fully, how it differs. I can find out and give you the answer later, but the answer is yes, it does differ.
Okay, brilliant. Another one from Peter. Okay, so if I can't do async inside async, what if I try traditional threading inside async, or any combination?
So the question was if you do async in async. So you can do nested async. So if you have a method called async task run async, you can have another asynchronous method, a completely different asynchronous method being called within that. And you can even use threading, and you can do tasks. You can do everything inside an asynchronous method that you could do in a non-async method.
Fantastic. And one of the things I certainly learned the benefits of is when playing around, instead of thread.sleep, using task.delay instead.
Yep.
And how that returns control back, whereas thread.sleep essentially kills your thread as it goes.
For sure, yep.
Yeah. Another one from Brett here just saying thank you for the presentation, very informative.
Oh, thank you.
A question I have, our strongest area is WPF and Windows Store apps and whatnot. But so I'm weaker in ASP.NET. But when I was originally learning it, delivering anything to the thread pool using task.run in ASP.NET was potentially dangerous because of what it can do to IIS. Is there something you could add to that, maybe?
Yeah, so in ASP.NET, you can also do the configure await, which will kind of notify you where to return back to when the asynchronous operation is done. So doing async and await or asynchronous programming in ASP.NET does differ a small bit because it captures this synchronization context to kind of know where it needs to communicate back to. So a way to say that it doesn't have to return to the same context as the caller is to do configure await false. And I see a lot of ASP.NET developers doing that to avoid deadlocking or avoid unreliable behaviors in their applications.
So I understood that can cause a lot of harm to IIS in its thread pool management. That's then from the early materials when I first took it up.
Yep.
Just a message from Jeff. Excellent presentation. It was really helpful to have the wrap up at the end to reinforce the concept you covered.
Thank you very much.
Okay, if you want to put your contact details back up for us, please, Philip.
Sure, yeah. Thank you all for coming. It's been lovely talking to you all. And if you do have any questions after this, if you do have any problems with Async and Await, please do feel free to ping me on Twitter or send me an email. You can just ping me on Twitter and I'll send over my email details.
Fantastic.
Yeah, so thank you all.
Okay. If anybody wants to take that down and catch Philip on Twitter, I'm sure he'll answer any more questions that you have there. And thank you very much for a great presentation, Philip. It's certainly an area that I enjoy a lot. And I've certainly played around, especially with the Windows Store apps and Windows Phone, where UI responsiveness is a key thing.
Yeah, it's an interesting topic, and it's turning up, even if it's been around for a long time, it's kind of turning up even more now with even more rich clients. And now that you can do .NET on kind of any platform, it turns up in more scenarios than you might have expected a few years ago. So it's really an interesting topic, and it's really one of the things you need to get your head around, I guess, to write good applications.
Oh, thanks very much. Really appreciate it.
Thank you for having me.
Okay. Right. You're welcome. Most welcome. No one else has got anything else to add there. Just before Philip heads off, just want to say thank you to our sponsors again, SyncFusion, Pluralsight, Telerik, and all the help that they give us, AuxWeb. Without them, of course, we can't do what we do. And a big thank you from all the staff, and we very much thank you for all those who attended. And these presentations are for you, and we certainly enjoy bringing them to you. Thank you very much.